So if I told you to, like, take the tiny annoying buzzer out of your microwave, hike out into the woods, and use it to start a campfire, you would probably think I completely lost my mind.
Yeah, I mean, most people would just look at you and say, that's a speaker. I need a lighter.
Exactly. But physically speaking, like at the level of atoms and electrons, your microwave beep and the spark-producing lighter you use for your candles are, they're the exact same machine.
It is honestly one of the most profound illusions of modern life. You know, we walk through our homes and we see what looks like this world of absolute functional isolation.
Right, just a bunch of isolated boxes.
Exactly. A fan spins, a lighter sparks, a solar panel just, sits there on the roof. They don't seem to speak the same language at all.
They're all doing their own highly specific, separate things. But then you step into the world of solid-state physics, and suddenly that illusion of isolation just completely shatters.
It really does. It breaks down entirely.
Welcome to the Deep Dive. Today we are exploring a truly mind-bending text on the reversible symmetry of solid-state physics.
And our mission for you today is to, completely upend how you view the physical world around you.
Yeah, we're looking at the secret family reunion of the technological landscape, basically.
The foundational premise we're dissecting today is this really elegant, almost poetic rule of the universe.
Okay, let's hear.
So, in material science, there's this beautiful reversible symmetry.
Yeah.
The core rule states that if applying a specific external energy to a material creates electricity, then taking electricity and forcing it back into that exact same material will perfectly recreate that original external energy.
So it's basically a perfect two-way street. If you push it, it makes power. If you power it, it pushes.
Precisely. That is exactly it. And to truly understand why this happens, not just the what, but the how and the why, we're going to look at 4 fundamental pairs of everyday technology.
Right, going from the huge stuff to the tiny stuff.
Yeah, we'll start from the macro world of massive infrastructure and zoom all the way down into the quantum mechanical behavior of electron orbitals.
Which sounds intimidating, but we're going to break it down.
We absolutely will. We'll see how energy flows in one direction to become generation, and how it flows in the exact opposite direction to become consumption.
So let's start with something highly intuitive, something we can actually, watch happen with our own eyes. Let's look at mechanical energy.
Perfect starting point.
The twins here are the wind turbine, or really any mechanical electrical generator, and the humble electric motor.
Right, and this is a great place to start because it strips away the exotic quantum mechanics for a moment and just focuses on classical physics, specifically electromagnetism.
Because to the average consumer, a wind turbine is this monolithic piece of energy infrastructure, right? And a motor is just that tiny humming thing inside your electric toothbrush.
They look totally different. But if you crack them open, the architecture is actually identical.
Like completely identical.
Completely identical. At their core, both consist entirely of this carefully arranged relationship between permanent magnets and coiled conductive wire.
Usually copper wire.
Right. Yeah, usually copper. That is the beating heart of both machines. The only real variable is the direction in which the energy is forced through the system.
Okay, so let's trace the causality of that first direction. Let's say we have a massive offshore wind turbine. The wind blows, spinning those huge composite blades.
Right.
How does that purely physical kinetic energy turn into an electrical current?
To understand this, we kind of have to look back to the 1830s, to Michael Faraday's discovery of electromagnetic induction.
Okay, Faraday.
Yeah, Faraday realized that electricity and magnetism aren't separate forces. They are essentially 2 sides of the exact same coin.
Interesting.
So inside that turbine, you have permanent magnets creating a really stable, invisible magnetic field. And nature, generally speaking, favors equilibrium.
Right, it likes the status quo. It doesn't want things to change.
Exactly. It wants things to stay calm. But when the wind forcefully spins the propeller, it mechanically forces that coiled copper wire to rapidly rotate right through that established magnetic field.
So you're violently disrupting the calm.
You are. And this movement subjects the electrons inside the copper wire to what is known as the Lorentz force.
The Lorentz force. Okay, let's make sure we clearly define that for the listener. What is that exactly?
Well, the Lorentz force dictates that a charged particle, like an electron, moving through a magnetic field will experience a physical push.
Like an actual shove.
Yeah, a physical push perpendicular to both its direction of motion and the magnetic field lines. Because the copper wire is being forced to spin through the field, the electrons inside are subjected to this constant perpendicular push.
So they're just getting physically shoved down the length of the wire.
Exactly. And a synchronized directional flow of electrons is the literal definition of an electrical current.
I see. So we force movement, the magnetic field translates that movement into an electron push, and boom, we get power.
Precisely. We are using the wind's kinetic energy to forcefully disrupt the magnetic environment. And the universe's mechanical reaction governed by Faraday's law is to drive those electrons forward.
That's the electromotive force, right?
That's it. That's how a bicycle dynamo lights up when you pedal. And it's how a multi-megawatt offshore wind turbine powers an entire city grid.
Okay, so that makes perfect sense. But the thesis of our deep dive today is reversible symmetry.
Right.
So what happens if the air is dead still and we apply the electricity ourselves?
This is where we invert the physics. We move from Faraday's induction to the motor effect, which is governed by Ampere's force law.
Okay, so we're flipping the script.
We take that exact same internal setup, the permanent magnets and the copper coil, but this time we hook the copper wire up to a battery or the power grid.
We forcefully inject an electrical current into the coil.
Right. So now the electrons are moving first rather than being moved by the physical spinning.
Got it. And when electrons flow through a coiled wire, what happens?
Well, that coil actually generates its own magnetic field. It temporarily becomes an electromagnet, complete with its own north and south pole.
Oh, wow. And because this newly created electromagnet is sitting inside the permanent magnetic field of the machine's housing,
It creates an immediate physical conflict.
because you have two magnetic fields fighting each other.
Exactly. If the coil's new temporary north pole is facing the permanent north pole of the housing magnets, they violently repel each other.
Like when you try to push two magnets together and they slide apart.
Just like that. This repulsive force pushes the coil, but because the coil is mounted on an axle, that push translates into rotational movement.
It spins.
It spins. And as it spins, the internal wiring, often using a component called a commutator, constantly flips the direction of the electric current,
Wait, why does it flip the current?
because that flips the magnetic poles. So the coil is always being repelled and pushed forward, never finding that equilibrium.
So it just chases its own tail endlessly, spinning the axle.
Right. And that mechanical spinning is what turns the wheels of an electric vehicle, or spins the drum of your washing machine, or rotates the blades of your desk fan.
I think the most striking real-world application of this specific symmetry is regenerative braking in electric vehicles.
Oh, absolutely.
I mean, it's one thing to talk about turbines and fans abstractly, but if you drive an EV, you are literally experiencing this reversible symmetry every single time you hit a red light.
That is the perfect modern example. When you press the accelerator in an EV, you are pulling electricity from the battery and dumping it into the induction motor.
You're operating in motor mode.
Right.
Hmm.
The battery forces the current, the electromagnets repel, the axle spins, and the car moves forward.
But the second you take your foot off the accelerator,
The whole system instantly flips.
this automatically.
Instantly, the battery stops sending electricity. But the car is heavy, right?
No.
And it's still rolling forward at 60 miles an hour.
Right, it has massive momentum.
So that kinetic momentum forces the wheels to keep turning, which forces the axle to keep spinning, which forces the copper coils to spin through the magnetic field.
Which is the exact definition of a generator.
Exactly. The motor instantly becomes a generator. The kinetic energy of the heavy moving car is now doing the work of the wind.
That is wild.
It spins the coil, forces the electrons to move via the Lorentz force, and pumps electricity backward into the battery to recharge it.
And because pushing those electrons through the magnetic field actually requires physical work, it creates mechanical resistance, right?
Yes, and that resistance is what physically slows the car down without you even having to touch the brake pads.
That is brilliant. The car slows down because the kinetic energy is literally being consumed to create electricity.
Exact.
But wait, let me push back on this a bit. Because if they are perfectly symmetrical, why do we bother manufacturing separate motors and generators?
Okay, fair question.
Like, if I rip a ceiling fan out of my house and stick it in a hurricane, is it going to power my television efficiently?
Efficiently? No, definitely not. And that brings up the engineering reality of the symmetry.
The catch.
Right. While the underlying physics are perfectly reversible, the engineering is highly specialized. A ceiling fan is optimized to move air, not harvest it.
Okay, so the shape is wrong.
The pitch of the blades, the thickness of the copper wire, the gear ratios, Everything is tuned to minimize electrical resistance and maximize airflow.
So it's purely a matter of optimization.
Right. If you stuck a ceiling fan in a hurricane, the wind would indeed force the motor to act as a generator. It would push electricity backward down its own power cord.
Really? It actually would.
It would. But because the coil windings aren't optimized to handle that kind of load, and the aerodynamics of the blades are wrong for harvesting wind, it would be terribly inefficient.
It would probably just break.
It would generate a tiny amount of power before the mechanical stress probably just destroyed the plastic blades entirely.
So the physics is universal, but
Yeah.
the engineering is highly localized.
Precisely.
Still, it completely changes how you view your household appliances. I mean, every blender, every power drill, every hair dryer, they're all just generators sitting in disguise, waiting for you to physically spin them.
It's a profound realization. What we call generation and consumption are not actually different technologies. They are just the exact same machine experiencing energy flow in opposite directions.
Wow. Okay, but mechanical spinning is relatively straightforward. Moving parts are easy to visualize.
They are.
However, moving parts wear out. Bearings fail, friction creates heat, mechanical systems inevitably break down.
Sure, classical mechanics has its limits.
So what happens when we strip away the macro scale movement entirely? What happens when we shrink down to the atomic level where things don't spin, but rather, well, they emit or absorb electromagnetic radiation?
This transition moves us directly from classical electromagnetism into the realm of quantum mechanics and solid-state physics.
Our second pair of twins.
Yes, the solar panel and the LED.
Now, to the naked eye, these look like they belong to entirely different eras of technology.
Right.
I mean, a solar panel is a massive, dark, flat slab of glass absorbing the sun on a roof. An LED is a microscopic, piercingly bright point of light in your TV screen.
They seem like total opposites. One is black and absorbs light, the other is bright and emits light.
But if you look at their internal architecture under an electron microscope,
You will find they're built from the exact same semiconductor crystals. Specifically, they both rely on a microscopic structure called a PN junction.
let's really dig into this because I don't want to just gloss over the quantum stuff. What exactly is a PN junction and why is it so crucial to this reversible symmetry?
To understand a PN junction, we first have to understand the semiconductor itself. Usually, this is silicon.
Okay, silicon, like the valley.
Exactly. Pure silicon forms a very stable crystal lattice. Every silicon atom shares its 4 outer electrons perfectly with its 4 neighbors.
So it's locked down tight.
It's a tight, happy, crystalline structure where no electrons are free to move. And because no electrons can move, pure silicon is actually an insulator. It doesn't conduct electricity at all.
Wait, really? Then how do we make it conduct to use in electronics?
We have to intentionally introduce impurities.
We break it.
Kind of. This process is called doping. We take 1/2 of our silicon crystal and dope it with an element like phosphorus, which has 5 outer electrons instead of 4.
Okay, so when the phosphorus atom forces its way into the silicon lattice, it has 1 electron left over that just doesn't fit into those neat molecular bonds.
Exactly. That extra electron is now free to roam around the crystal. Because electrons carry a negative charge, we call this the N-type side of the semiconductor.
N for negative, got it.
Now we take the other half of the crystal and dope it with an element like boron, which only has 3 outer electrons.
So it's actually missing an electron to complete the lattice.
Right. It creates a literal absence of an electron, which physicists call a hole.
A hole, just empty space.
Just empty space. But even though a hole is just empty space, it behaves mathematically exactly like a positively charged particle.
Oh, that's weird.
It is weird. But because of that, we call this side the p-type side, for positive.
Okay, so we have N-type silicon packed with free negative electrons and P-type silicon packed with positive empty holes.
And the magic happens right where those two sides touch. That boundary is the PN junction.
The border zone.
Exactly. When you smash them together, some of the free electrons from the N side immediately rush across the border to fill the empty holes on the P side.
They just want to find a resting place, right?
Yes. But in doing so, they create a permanent built-in electric field right at the border. This border zone is called the depletion region.
So it's like a barrier.
It acts as a massive microscopic barrier. We can visualize it as a steep electrical hill or a band gap.
Electrical hill, I like that visual.
Once this hill is established, the rest of the electrons on the N side just don't have enough energy to climb it. The system reaches equilibrium and everything stops.
Okay, so we have built the stage. We have our electrical hill. How does sunlight hitting this dark piece of silicon actually create power?
Let's trace the photoelectric effect. Sunlight isn't just a continuous wave. It's composed of fundamental, quantized packets of energy called photons.
Little packets of light.
Right. Imagine a photon traveling from the sun, plunging into the solar panel, and striking an electron that is resting quietly near that depletion region, right near the bottom of that electrical hill.
Okay.
If the photon has the right amount of energy, an amount greater than the band gap of the silicon, it transfers all of its explosive energy directly into that electron.
Like a microscopic, highly energetic game of billiards. The cue ball hits the 8-ball.
That is the perfect analogy. That explosive transfer of energy jolts the electron. It violently breaks free from its atomic bond, creating a new electron-hole pair.
Oh, wow.
And because this happens right inside that built-in electric field, that steep hill, the electron is immediately swept forcefully down one side of the hill while the hole is swept to the other.
They are forcibly separated by the architecture of the crystal.
Precisely. The electron is now trapped on the end side with very high potential energy. It desperately wants to recombine with a hole to achieve a lower energy state.
But the electrical hill in the PN junction blocks it from just crossing back over, right?
Exactly, it's stuck.
So we give it an alternate route.
Right. We attach a conductive metal wire to the end side, run it out of the solar panel through your house to power your refrigerator or charge your phone, and then route it back to the P side.
A massive detour.
Yes. The electron takes this external bypass route to get back to the holes.
And an electron traveling through a wire, doing physical work along the way, is electricity.
You've got it. The photon kicks the electron out of its bond, the internal electric field sweeps it away, and its long journey back home through our external wire is what we harvest as solar power.
That is incredibly elegant, just beautifully simple once you understand the hill.
It really is.
But now we have to reverse it. If a solar panel takes light to push electrons through a wire, then the LED must take electrons pushed through a wire to create light.
Exactly. This is the phenomenon of electroluminescence.
Electroluminescence.
We take that exact same PN junction, the exact same electrical hill, but instead of letting it sit in the sun, we put it in the dark.
Okay.
We hook it up to a battery, and we apply what is known as forward bias.
Meaning we are applying external voltage to the crystal.
We use the battery to forcefully pump millions of electrons into the N side of the crystal, while simultaneously pulling electrons out of the P side, which creates more holes.
So we are artificially cramming electrons and holes toward that central electrical hill.
We are applying immense electrical pressure. The battery provides so much energy that the electrons are violently shoved up and over the electrical hill, right into the P side where all those empty holes are waiting.
Oh man, so they recombine, the electron drops into the empty seed.
Right. But remember the physics here. To be pushed over that hill, the electron had to be in a highly excited, high-energy state.
Because we shoved it up there with a battery.
Exactly. When it finds a hole and drops into it, it falls back into a low-energy resting state. And the law of conservation of energy states that energy cannot be destroyed.
So it has to go somewhere.
Exactly. When the electron drops into that hole, it must shed all of its excess energy.
Let me guess. It sheds that energy as a photon.
Exactly. The excess energy is instantaneously ejected from the crystal as a photon of light.
Wow.
You force the electrons over the hill, they drop into the holes, and every single drop releases a photon. Millions of electrons dropping millions of times a second creates the piercingly bright light of an LED.
Okay, I have a question about this, because my understanding of thermodynamics is that there's always a tax to pay, right? Entropy.
Sure.
When you force electrons to do work, you usually get heat. I mean, in an old incandescent light bulb, we forced electricity through a tungsten filament, and it generated so much heat that it just happened to glow white hot as a byproduct.
A very inefficient byproduct.
Right. So how does forcing electrons over a microscopic hill in an LED not just melt the crystal? How does it specifically create pure light instead of mostly heat?
That is a brilliant question, and it cuts to the core of why solid-state physics revolutionized the entire world.
Okay, let's unpack it.
In an incandescent bulb, like you said, you rely on thermal radiation. You are literally just heating metal until it glows, which is incredibly inefficient. 90% of the energy is wasted as heat.
Just totally wasted.
But in an LED, we are relying on quantum mechanics. The band gap, the specific height of that electrical hill, is fixed and highly specific.
Okay.
When When the electron drops across that band gap, the energy difference translates directly into a photon with a specific wavelength. It's called radiative recombination.
Radiative recombination.
Because it's a direct quantum jump, almost all the energy goes straight into creating the photon, not vibrating the crystal lattice, which is what causes heat.
Oh, I see. So it's bypassing the thermal middleman entirely. It doesn't need to get hot to glow.
Exactly. Now, no system is perfectly efficient, of course. Some electrons get caught on impurities in the crystal and release their energy as heat, which physicists call phonons instead of photons.
Right, phonon.
This is called non-radiative recombination, and it's why high-powered LEDs still need those little metal heat sinks on the back. But compared to an incandescent bulb, an LED is an absolute masterpiece of directed energy.
And the height of that band gap determines the color of the light.
Precisely.
Yeah.
And this is why the Nobel Prize in Physics was awarded in 2014 for the invention of the blue LED.
Why blue specifically? Why not red or green?
Well, red and green LEDs were easy. The band gaps required materials that were relatively easy to crystallize, like gallium arsenide. But a blue photon requires a much higher energy drop.
Because blue light is higher frequency, higher energy on the spectrum.
Right. To get a high enough electrical hill to produce a blue photon, scientists had to use a material called gallium nitride.
And I'm guessing that was hard to make.
Extremely hard. Growing perfect gallium nitride crystals without microscopic cracks and defects was considered practically impossible for decades.
Oh, wow.
The lattice mismatch between the substrate and the crystal caused constant failures. But when researchers finally figured out how to grow a clean gallium nitride crystal, it allowed us to create blue light.
And when you mix blue, green, and red light?
You get pure white light. Exactly. The blue LED gave us the modern smartphone screen and the white LED light bulbs that are currently drastically reducing global energy consumption.
That is just nuts. But coming back to the reversible symmetry, the text highlights a real-world application of this specific pair that just blew my mind.
Oh, the quality testing.
Yes, because they are twins, the solar panel on your roof is technically also a giant, flat LED.
It is entirely true, and it's a phenomenon called electroluminescence. If you wait until the dead of night so there is zero sunlight acting on the panel to push the electrons,
Right.
and you hook a massive power source up to the output cables of your solar panel, pushing a massive electrical current backward into the system.
You are artificially shoving those electrons up the hill.
You are artificially forward biasing the massive PN junction of the solar panel. The electrons will cross the depletion region, drop into the holes, and release photons.
That's wild.
If you have an infrared camera, or if the band gap is right for visible light, you will actually see the entire solar panel glow with a faint light.
A solar panel acting as a giant dark sky flashlight.
And here's the truly fascinating part. The solar manufacturing industry relies on this exact reverse reaction every single day.
Because when you manufacture a massive silicon solar cell, how do you know if there are microscopic cracks or defects in the crystal lattice that will ruin its efficiency, right?
Exactly. You can't just look at it with a magnifying glass. It's a giant black slab.
So you force the panel to act like its twin.
In the factory, they pump heavy electricity backward into the newly manufactured solar panels, forcing them to light up via electroluminescence.
And then what? They take a picture.
They photograph the glowing panel with specialized cameras. Wherever there is a microscopic scratch, a broken lattice, or the dead zone, the electrons can't recombine properly.
So it won't glow in that specific spot.
Right. It shows up as a harsh, dark shadow on an otherwise perfectly glowing panel. They literally use the hidden symmetry of the LED to quality test the functional integrity of the solar panel.
That is just, it's breathtaking. You have the multi-billion-dollar solar industry racing to harvest the sun, and the massive LED industry lighting our homes.
Yeah.
And beneath all the stock prices and the marketing, it is literally the exact same electron commuting back and forth across the exact same microscopic hill.
It is the absolute poetry of solid-state physics. Whether you're generating power from the sun or illuminating a dark room, you are merely managing the commute of that electron.
Okay, my paradigm is thoroughly shifted. We've seen the macro symmetry of physical movement with Faraday's generators and motors.
Right.
We've seen the quantum symmetry of light with solar panels and LEDs. But what about the invisible comfort in our homes?
Temperature.
Exactly. What about temperature? Light is just one form of radiation, heat is another.
Yeah.
Can we coax electrons into carrying raw thermal energy the exact same way they carry light?
This brings us to a slightly more exotic pairing, but one that is absolutely foundational to modern high-performance engineering. We are looking at our third pair, the thermal twins.
Lay it on me.
We are talking about thermoelectric generators and Peltier devices.
Okay, let's set the table. On the generation side, we have the thermoelectric generator, which turns a difference in temperature, heat gradient, into electricity.
Correct.
And on the consumption side, we have the Peltier device, which takes electricity and uses it to violently separate hot and cold temperatures.
And just like our solar panels, these rely entirely on solid-state semiconductor physics, but with very specific, highly engineered alloys.
Like what kind of alloys?
The most common are bismuth telluride or bismuth antimony alloys.
Okay, to understand how these alloys work, the text provides a metaphor that I found extremely helpful.
The porters.
Yes. When dealing with these specific bismuth alloys, we shouldn't just picture electrons as tiny abstract spheres of negative charge. We needed to visualize the electrons acting as porters.
Like Sherpas or mountain guides carrying heavy backpacks.
Exactly. Imagine a microscopic crew of porters carrying heavy backpacks. But in this specific thermal landscape, their backpacks are filled with heat.
It's a great visualization.
The electrons literally physically carry thermal energy as they move through the crystalline material. Let's look at the generation side first.
The Seebeck effect.
Right. This relies on something called the Seebeck effect, discovered way back in the 1820s. How does exposing a piece of metal to heat generate an electrical current?
Thomas Johann Seebeck discovered this almost accidentally. If you take a piece of conductive material, let's use our highly engineered bismuth telluride chip, and you expose one side of it to a severe heat source, like a hot exhaust pipe.
Okay, so one side is super hot.
While keeping the other side exposed to freezing cold air, you create a steep temperature gradient.
Hot on the left, cold on the right.
Now think about what heat actually is at the atomic level. Heat is just kinetic energy. It's vibration and movement.
Right, atoms jiggling.
The free electrons on the hot side of the chip absorb that thermal energy. Physicists sometimes refer to these free electrons in a metal as an electron gas.
An electron gas, okay.
When you heat a gas, it expands. The electrons on the hot side get hyperactive, they gain high kinetic energy, and they naturally begin to diffuse or expand away from the heat source.
So they're moving away from the heat.
Yes, relentlessly migrating toward the cold side of the chip where the energy is lower and things are much calmer.
They're literally fleeing the heat.
Yes. But let's recall our foundational definition from the very first mechanical segment. What is a synchronized mass directional movement of electrons?
It's electrical current.
Precisely. Because the temperature gradient forces this massive synchronized migration of electrons from the hot side to the cold side, it naturally generates an electromotive force.
It creates a voltage.
Exactly. If you attach wires to both sides of the chip, you can harvest that moving stream of electrons to power a device. You provide a temperature difference, and nature gives you power. That is the Seebeck effect.
And this isn't just theoretical either. I mean, this is how we powered deep space probes, right?
Absolutely. Think about the Voyager probes, which are currently billions of miles away in interstellar space.
Right, way past Pluto.
They cannot use solar panels. The sun is just a faint, tiny star out there. Instead, they use radioisotope thermoelectric generators, or RTGs.
RTGs, how do those work?
They have a lump of decaying plutonium that naturally generates intense, constant heat, and the cold vacuum of space provides the cold side.
Oh, wow.
The massive temperature difference across the thermoelectric materials inside the RTG constantly drives electrons from the hot plutonium toward the cold hull of the ship,
Generating electricity.
generating the exact electricity that has kept those probes transmitting data back to Earth for nearly half a century.
That is awe-inspiring. A hunk of hot metal and the cold vacuum of space, separated by a crystal, powering our reach into the cosmos.
It's incredible engineering.
But okay, if we're adhering to our rule of reversible symmetry, we have to flip the script. If a temperature gradient pushes electrons to create power, then pushing electrons with power must create a temperature gradient.
And this is the Peltier effect, discovered just a few years after Seebeck by Jean-Charles Athanase Peltier.
So we run the system in reverse.
Exactly. We don't provide external temperature this time, we provide the electricity. You take that exact same bismuth telluride chip, resting quietly at normal room temperature,
Just sitting on a desk.
and you apply a strong, direct electrical current from a battery.
So I am essentially cracking a wick on these electron porters. I am using voltage to force them to march in one specific direction across the chip.
That is a very vivid way to put it, but yes, By applying a heavy voltage, you force the electrons to cross the microscopic junctions between the p-type and n-type semiconductor materials inside the chip.
Okay, so they're marching.
But here is where the thermodynamics come into play. When an electron is forced from a low-energy material state into a higher-energy material state across that junction, it needs extra energy to make the jump.
Where does it get?
Where does it get that energy? It absorbs it from the surrounding environment in the form of heat. Specifically, it absorbs phonons from the crystal lattice.
It packs the heat into its backpack.
Exactly. As this forced march happens, the electrons physically strip ambient heat energy away from the side of the chip they are leaving.
Wow.
They absorb it, carry it across the microscopic landscape of the alloy, and when they cross the next junction back into a lower energy state, they dump all of that absorbed heat onto the arriving side.
So what happens to the physical piece of metal sitting on the table?
It's dramatic. Within seconds, the side of the chip the electrons are fleeing from becomes instantly violently cold.
Really? Just from electricity?
It will literally accumulate frost from the moisture in the air because all its thermal energy was just stolen by the migrating electrons.
That is wild.
Meanwhile, the side of the chip the electrons are arriving at becomes burning hot as all those microscopic backpacks of heat are dumped there all at once.
So by just running a steady electrical current through a solid, completely silent piece of metal, you create a freezing side and a burning side.
Exactly.
If you've ever felt the back of your refrigerator, you know it's dumping heat into your kitchen to keep the inside cold.
Right.
But a traditional fridge uses a loud, buzzing mechanical compressor to pump chemical refrigerants through tubes. The Peltier device has absolutely no moving parts, no refrigerants, no liquids, no noise.
Nothing. It's just a solid piece of metal manipulating heat purely through electron traffic.
And you interact with this reverse reaction all the time, don't you?
You do. If you have a high-end, custom-built PC, the processor gets incredibly hot. Many enthusiasts use silent Peltier coolers mounted directly onto the CPU.
Oh, to keep the computer from melting.
Right. The cold side of the chip is pressed against the processor, chilling it to near freezing temperatures, while the hot side faces a heat sink and a fan to blow the dumped heat away.
What about those tiny wine fridges?
Yes, those tiny, ultra-quiet, portable wine refrigerators or the little cooler you plug into your car's cigarette lighter for road trips, they don't have buzzing compressors. They just use a solid-state Peltier chip.
But wait, I have to ask about the material itself, because you mentioned we use bismuth telluride alloys. Why bismuth? Why can't we just do this with a cheap piece of copper wire?
It's a great question.
If I run electricity through copper, why doesn't one end get freezing cold?
This brings us to one of the most fascinating engineering paradoxes in material science. To be a highly efficient thermoelectric twin, a material must possess a delicate, almost contradictory balance of properties.
A paradox? Like what?
It relies on a paradigm scientists call the phonon glass electron crystal, or PGEC.
Phonon glass electron crystal. Unpack that for me.
To work perfectly, the material must do two things that normally contradict each other. First, it must conduct electricity extremely well, so the electron porters can march easily without resistance.
It must act like a perfect crystal for electrons.
Exactly. But second, the material itself must be terrible at conducting heat naturally. It must act like shattered glass when it comes to phonons, which are the microscopic vibrations that carry thermal energy.
Wait, if the material is terrible at conducting heat, how does the heat move?
We only want the electrons to carry the heat in their backpacks.
Oh, I see.
If the material itself conducts heat well, like copper does, then the intense heat dumped on the hot side would just bleed right back through the metal to the cold side, ruining the gradient.
The heat would leak backward naturally faster than the electrons could actively carry it away.
Exactly.
Oh, it's like trying to bail water out of a sinking boat using a bucket. But the boat has a massive hole in the floor.
That's a perfect analogy.
You need material where the boat itself is perfectly watertight, so heat can't travel through the floorboards. But the electrons are free to carry buckets of heat over the side.
That is exactly it. Copper is too leaky. It conducts heat beautifully, which completely ruins the effect. Bismuth telluride has this miraculous, delicate balance.
So it's perfectly tuned for this.
Yes. Its heavy, complex, crystal lattice severely scatters phonons, fiercely resisting normal heat transfer. But its electrical structure allows electrons to glide freely. It forces the heat to only move via the electron porters.
Man, just think about the implications if we can refine these materials even further.
The potential is staggering.
Right now, so much energy is wasted as ambient heat. car engines, factories, even our own bodies. Imagine a future where the fabric of your clothing uses the Seebeck effect to harvest the temperature difference between your body heat and the cold winter air,
Yes.
generating enough electricity to keep your phone perfectly charged in your pocket just by standing outside.
The field of energy scavenging is massively invested in exactly that. A principle that silently cools a desktop PC can, in reverse, power the wearable technology of the future simply by harvesting human body heat.
Okay, we have elegantly manipulated magnetic fields to make power. We've elegantly bounced electrons across quantum band gaps to make light. And we've elegantly coaxed electron porters to carry heat.
We have. It's all very refined.
But what if we drop the elegance entirely? What if we don't want to rely on delicate temperature gradients or the subtle physics of photons? What if we want to use sheer brute physical force?
Sometimes brute force is exactly what the physics demands. And this brings us to our final and perhaps most baffling pair of twins.
We are looking at the structural twins, the everyday push-button lighter, and the electronic buzzer, or speaker.
Fire and sound.
Yeah. If you look at a cheap dollar store push-button lighter used for a barbecue, and the tiny speaker making your microwave beep when your coffee is hot, they seem utterly, hopelessly unrelated.
They do. But if you dismantle them, beneath the plastic casing, they both rely on the exact same structural heart.
What's in there?
A tiny, carefully manufactured piece of piezoelectric ceramic. Most commonly, it's a crystal known as barium titanate.
Let's start with the lighter, the generation of a massive electrical spark. This relies on the piezoelectric effect, famously discovered by the Curie brothers Pierre and Jacques in 1880.
Right.
How does pushing a plastic button create fire?
When you press the button on that lighter, you notice it requires a bit of effort, right? And it ends with a loud, heavy click.
Yeah, it snaps.
You aren't just completing a soft electrical circuit like a computer keyboard. You are actually physically compressing and releasing a tiny...
So there's actual physical violence happening inside the lighter.
Very much so. That tiny hammer releases and violently strikes the barium titanate crystal resting inside. It delivers a sharp, physical, crushing blow to the crystal lattice.
Okay, so we smash a crystal with a hammer. How in the world does a mechanical compression create a high-voltage electrical spark?
To grasp this, we must look deeply into the molecular architecture of barium titanate. It has a specific crystal structure known as a perovskite structure.
Perovskite, okay.
In a perfectly symmetrical crystal like diamond or salt, the center of all the positive electrical charges and the center of all the negative electrical charges perfectly overlap.
They cancel each other out, right?
Exactly. They cancel each other out, leaving the crystal electrically neutral.
It's perfectly balanced.
But barium titanate is asymmetrical. At room temperature, the central positively charged titanium ion is slightly off-center inside its crystalline cage. It sits just a little bit too high.
Oh, so it's intrinsically unbalanced.
Right. This natural asymmetry creates what physicists call a built-in dipole moment. One end of the molecular unit is slightly positive, and the other is slightly negative.
Okay, but it's still just sitting there.
Right. But when that tiny mechanical hammer violently strikes the crystal, it physically crushes the lattice. It squishes the crystalline cage.
And what happens to the charge?
This sudden traumatic compression physically forces that positively charged titanium ion to shift its position relative to the negatively charged oxygen atoms surrounding it.
You are physically shoving the electrical charges apart.
Exactly. The crushing force physically separates the centers of positive and negative charge on a macroscopic scale across the entire crystal.
And nature doesn't like that.
Nature absolutely hates this kind of sudden electrical imbalance. To instantly correct this traumatic distortion and reestablish equilibrium, the surface of the crystal practically hemorrhages the displaced electrical charge.
It bleeds electricity.
It violently expels an instant surge of electricity.
It just dumps the voltage to save itself.
Yes. And because the internal crystalline shift happens instantly across millions of unit cells, the voltage spike is massive.
How massive are we talking?
We are talking about thousands, sometimes tens of thousands of volts of electricity generated in a fraction of a millisecond, purely from a few millimeters of physical compression.
Thousands of volts.
Yeah.
From my thumb pushing a button.
Yes. And that massive voltage potential needs somewhere to go. It travels up a tiny wire to the tip of the lighter where there is a small gap of air.
And then it jumps the gap?
The voltage is so high that it literally rips the electrons off the air molecules in that gap, turning the air into conductive plasma.
And we see that plasma as a spark.
A spark that ignites the butane gas, giving you fire.
I just love how beautifully barbaric that is. I mean, every time I light a candle on a birthday cake, I am acting as a microscopic blacksmith.
You are.
I'm literally crushing an asymmetrical crystal with a tiny hammer to summon miniature lightning.
It is exactly what you were doing. Mechanical pressure forces a massive electrical output. Now, apply our rule of reversible symmetry, the inverse piezoelectric effect.
Okay, let's flip it.
If physically smashing the crystal creates electricity,
Yeah.
then feeding it electricity should sash it.
Or at least physically warp it.
Exactly. If we take that exact same asymmetrical barium titanate crystal, we remove the hammer, and instead we apply an alternating electrical current to it.
Meaning we rapidly pump voltage in, stop, reverse polarity, pump it in again, thousands of times a second.
We subject the crystal to a rapidly fluctuating electrical field. Remember how the physical squeeze forced the titanium ion to move, creating a voltage?
Yeah, we physically shoved it.
Well, if you apply an external voltage, the electrical field violently pulls and pushes on that off-center titanium ion. The internal structure desperately tries to align with the fluctuating electrical field.
So the crystal is physically reacting to the electricity.
It causes the entire solid crystal to rapidly expand and contract. It physically twitches. It grows longer, then shorter, then longer, then shorter.
Wait, so when my microwave goes beep to tell me my food is ready, there isn't a tiny digital sound file playing through a traditional magnetic speaker cone.
None in those flat, simple buzzers, no.
I am actually electrocuting a crystal, and the crystal is physically writhing in place.
I laugh because that is remarkably accurate. You are hitting it with alternating voltage, say, 4,000 times a second.
Wow.
The crystal is rapidly expanding and contracting, flexing and bowing 4,000 times a second in exact time with the electrical pulse.
And how does that make sound?
Now imagine this crystal is glued to a thin piece of metal or plastic. As the crystal violently writhes and flexes, it forces that metal plate to flex with it.
Like a drumhead.
Exactly. This high-speed writhing physically pushes against the air molecules surrounding it. It beats the air exactly like the skin of a drum.
And those rapid changes in air pressure ripple outward through the kitchen.
And hit your eardrum.
And we perceive that mechanical air pressure as a beat.
Exactly. The mechanical vibration creates the acoustic sound waves we hear as the alarm on a digital watch, the piercing beep of a microwave, or the relentless buzz of a smoke detector.
That is incredible.
You apply alternating electricity, and the crystal physically dances to that exact rhythm, vibrating the air to make sound.
This has deep historical roots too, right? This isn't just about microwaves. The inverse piezoelectric effect changed the course of naval warfare.
You're referring to the invention of sonar during World War I. Absolutely.
How did that work?
Paul Langevin, a French physicist, used quartz, which is highly piezoelectric, to create the first acoustic submarine detectors. He applied high-frequency alternating current to massive quartz crystals submerged in the water.
The electricity caused the quartz to vibrate.
It vibrated so fast that it pushed the water, sending out high-frequency acoustic pings, ultrasound waves. Those waves bounced off the metal hulls of enemy submarines and echoed back.
And when the echo hit the crystal,
the physical pressure of the returning sound wave physically compressed the quartz, generating a tiny voltage via the forward piezoelectric effect, which the sailors literally listened to on their headsets.
the exact same crystal was acting as both the speaker to shout the sound and the microphone to listen for the echo.
Exactly. Simply by flipping the symmetry between generation and consumption. Modern medical ultrasound works on the exact same principle today.
I am truly never going to look at my digital watch the same way again. Every time that alarm goes off in the morning, a tiny crystal inside is violently writing to an electrical rhythm.
It perfectly encapsulates the dual nature we've been discussing for the past hour. You physically deform the crystal, it shouts electricity at a lighter. You shoot it with electricity, it physically deforms and shouts sound at the speaker. The entrance and the exit are just perfectly symmetrically flipped.
Let's zoom out and synthesize this incredible journey, because this has been a massive paradigm shift. We started at the macro level.
With the motors.
Right. We saw that the monolithic wind turbines generating power for our cities are the exact same electromagnetic machines as the tiny motors spinning the wheels of our EVs. It's just Faraday's induction versus Ampere's motor effect.
Magnets and copper.
Magnets and copper. Push it with a physical kinetic energy, you get moving electrons. Push the electrons, you get spinning kinetics.
Perfect summary.
Then we shrank down to the quantum realm. We explore the elegant PN junctions of silicon. The solar panels on our roofs and the LED lights in our living rooms are the exact same atomic hills.
Photons kicking electrons.
Exactly. Photons explosively kick electrons up the band gap to power our homes, and we forcefully pump electrons up the hill so they can drop back down, releasing photons to light up the dark.
And we saw how the solar industry cleverly exploits that exact reversibility, using electroluminescence to turn solar panels into giant glowing LEDs just to hunt for microscopic manufacturing defects.
Which is still my favorite fun fact of the day. And then we moved into the thermodynamic world of bismuth alloys.
The porters.
We watched the electron porters carrying backpacks of thermal energy. A temperature gradient, a hot side and a cold side, makes them forcefully migrate, generating the power that runs deep space probes.
A Seebeck effect.
But if we force those porters to march using an electrical current, they drag the heat with them, creating the silent solid-state refrigerators that cool our supercomputers.
The Peltier effect.
And finally, we drop the elegance for brute force, the structural symmetry of the perovskite crystals, smashing barium titanate with a mechanical hammer to abruptly shift its internal dipole moment, vomiting out thousands of volts to spark a lighter,
Violence and electricity.
versus hitting that same crystal with an alternating current so it physically writhes, beating the air to beep at us when our oatmeal is done.
If we pull all of these disparate physics together, the core philosophical thesis of the text we analyze becomes undeniably clear. The concepts of generation and consumption, which dictate how we structure our economies, how we build our power grids, how we market our appliances, are mostly illusions of human perspective.
They seem like entirely separate sectors of technology to us as consumers.
But when you look through the objective lens of solid-state physics, they are actually the exact same crystal, the exact same alloy, the exact same machine.
Wow.
The only defining difference is the direction the energy is flowing, forward or reverse, generation or consumption.
It is literally just the fundamental laws of nature playing in forward and then playing in rewind.
Exactly. And the text makes a wonderful, slightly philosophical concluding point. Discovering and hacking this beautiful, reversible symmetry in nature is not just a matter of utilitarian usefulness.
What else is it?
It is the ultimate puzzle and the ultimate triumph of human materials science. We find these fundamental, almost musical, symmetrical rules of the universe, and we twist them, dope them, and engineer them to fit our everyday needs.
So what does this all mean for you, the listener, right now? The next time you sit in your living room or your car or your office, I want you to truly look around at all those distinct gadgets.
The spinning fan, the bright lights.
The silent mini fridge, the beeping microwave. Realize that you aren't surrounded by hundreds of different, isolated, bespoke inventions. You are actually surrounded by just a handful of brilliant hacks of nature's inherent symmetry.
You are sitting inside a web of universal rules.
Universal rules just flowing in different directions depending on what we ask the electrons to do today. But before we wrap up, I want to leave you with a final provocative thought.
Oh, I like this one.
Something to really mull over that takes everything we've unpacked today and pushes it one speculative step into the future.
Let's hear it.
If all of these systems are perfectly physically reversible, if the dividing line between a generator and an appliance is just the direction of the electrical current, could we one day design a single universal twin device?
A completely unified metamaterial.
Exactly. Imagine building a smart wall panel in your home. It's made of advanced, hybridized solid-state metamaterials, a perfect blend of silicon PN junctions, bismuth telluride alloys, and piezoelectric ceramics.
The ultimate hybrid.
During the day, the summer sunlight hits it. The photons kick the electrons across the band gap, and it acts as your primary solar power generator.
And then night falls.
Right. At night, the sun goes down. Your smart home flips the current. It drives electricity backward into the panel, forcing the electrons to recombine. And that exact same pane of material begins to glow, becoming your room's ambient LED lighting.
Electroluminescence on demand.
Say it's a sweltering August afternoon. The internal chips use the massive temperature gradient between the hot exterior and the cool interior to generate even more power via the Seebeck effect.
Because of the heat difference.
But if you're feeling too warm inside, the house flips the current again. The electron porters engage the Peltier effect, relentlessly dragging the heat right out of your living room, acting as a totally silent, solid-state air conditioner.
This is an incredible vision.
And when you decide to throw a party, high-frequency alternating currents are pumped into the structural ceramics of the wall. The entire structure rhythmically flexes and writhes on a microscopic level, acting as a massive, invisible, high-fidelity stereo speaker.
You're replacing an entire house of appliances with one smart wall.
Could we eventually move away from manufacturing dozens of different plastic-encased appliances and just build our habitats out of programmable matter that simply flips nature symmetries forward and backward on demand?
That is the ultimate holy grail of mastering these materials. Once we completely dissolve the conceptual wall between generation and consumption, the possibilities for how we engineer our physical world become practically limitless.
We're not just building machines anymore.
No, we are no longer building machines. We are programming the physical environment itself.
And it all starts with understanding that the buzzer in your kitchen and the lighter on your grill are just two sides of the exact same coin.
Perfectly symmetric.
Thank you so much for joining us on this incredibly deep dive into the reversible symmetry of the physical world. Stay intensely curious, keep looking for those hidden symmetries hiding in plain sight around you, and remember, the next time you hear that microwave beep, just think of the writhing crystal. We will see you on the next deep dive.